All right, so it's working. So Yanju Chen will tell us about automated detection of under-constrained circuits in zero-knowledge proofs.
Yeah, thank you for the introduction, and thank you for joining the talk. I'm Yanju Chen from UCSB and Veridise. We'll be talking about how to check for a safety property in arithmetic circuits constructed for zero-knowledge proof. This is joint work with the awesome folks from UCSB, UT Austin, Harvard University, Complutense University of Madrid, UW, ZKonduit, Xerox PARC, and Veridise. Since we're talking about bugs in zero-knowledge circuits, here's an intuitive example about the idea behind zero-knowledge proofs, or ZK proofs. A ZK proof system allows users to prove statements while using but not revealing some secret information. So consider this example, where you and your friend wants to find Wally in the picture. You have knowledge where Wally is, but your friend doesn't believe you. So how do you prove to your friend that you know where Wally is without giving away his location? So one solution is you take a massive piece of paper to cover up the entire image, showing your friend the image of Wally throughout a cutout. In this way, you prove you really know Wally's location without revealing it to your friend, nor giving out the other information about Wally's location. So this is a simple analogy of how a zero-knowledge proof would work. With the help of many user-friendly cryptographic tools, developers can easily build security-sensitive applications with the help of zero-knowledge proofs without starting everything from scratch nowadays. So there are many interesting use case scenarios of ZK, from software's verifiable computation and file system control to hardware security like IoT security and privacy in supply chains. Besides, the nature of ZK proofs provides a brand new way for secured identity management, which becomes the core for applications like anonymous voting systems, secured messaging, and many cryptocurrencies. That is, users are able to authenticate themselves without worrying about revealing secret credentials. This also creates a broader impact on traditional industries like banking and gaming, as well as newcomers like public blockchains by enabling a new ZK layer that tackles with many long-enduring pains in privacy preserving. So as mentioned, creating a ZK circuit becomes easier and more user-friendly now. Here I'm showing you the brief workflow for creating a ZK circuit. First, the developer writes the desired program in a source language like Circom or Halo 2. And then the source code consists of two different parts, the witness computation and the constraints. So here you can think of a witness is similar to intermediate value generated from program execution that keeps record of part of the valid state of a program. Then the program is then compiled into two parts, the witness generator and a set of so-called polynomial field equations, which you can think of as a set of quadratic equations over the inputs, outputs, and intermediate values of the program. And finally, the field equations are transformed into a snark, which is comprised of a prover and a verifier. A key challenge for ZK developers is that writing their desired program requires writing both the witness generation code and a set of constraints, which are used by the compiler to produce the polynomial field equations. And critically, in order for the ZK program to be correct, the witness generation code and constraints should be equivalent. Today, we'll focus on bugs that arise from the mismatch between witness generation and constraints, and we'll demonstrate a variety of automatic techniques for helping developers avoid these bugs. So before we dive into the tooling, we must first understand what we mean for the witness generation and constraints to be equivalent. Let's first provide some definition. So let our witness generation code be a program P, which takes as input some value X and returns some value Y. And furthermore, let C be a system of constraints over X and Y, such that for some concrete values of X and Y, C produces either true or false. So given these definitions, what does it mean for P, the program, and C, the constraints, to be equivalent? So formally, we say that P and C are equivalent if for any input X to P such that P of X equals Y. X and Y satisfy C. So in other words, C values are true on X and Y. In other words, this definition comes with two requirements. So first, any input-output pair of the program P must be a satisfying assignment of the constraint C. And second, any pair of x, y which satisfy the constraint C must be an input-output pair of the program P. So the important question here is, how can this be violated? We'll break down violations of this equivalence property into two classes, one corresponding to each of the requirements that I just mentioned. The first type of violation is what we refer to as an overconstrained bug, which is where there is some input-output pair of the program which does not satisfy the generated constraints. And the second type of violation is what we refer to as an underconstrained bug, which is when there exists some pair of value x and y which satisfy the constraints, but they are not an input-output pair of the program. So this type of bug is quite common and will be the focus of this talk. So why do we care about this underconstrained bug? To understand this, recall the ZK circuit workflow that we presented in the previous slide. In the end, the procedure produces a snark, which is comprised of a prover and a verifier. Critically, if there is an underconstrained bug in the original source code, the verifier can accept bad inputs and outputs. This can lead to serious vulnerabilities in applications, including enabling attackers to drain all the tokens in the protocol or allowing users to double spend their funds. So now that we have a sense of the consequence of these bugs, let's go over a simple example of what kind of bugs they look like in the real code. Take this bug implementation of num2bit from Circom library. Num2bit takes as input a prime field element and constructs a binary representation of it using an array of n elements, which should be either 0 or 1s. The triple equal sign here indicates the constraints added by the developer, which say that the ith element of an array is either 0 or 1. And the bug in this implementation is the loop body uses n-1 as the upper bound instead of n. Here are the constraints generated for this bug in implementation, where n equals 3. Note that out2, this one is underconstrained. This means an attacker could pass in any value for out2 and still gets the proof verified. So to detect for such bugs, there are two strategies that we could immediately think of. The first strategy is to use an SMT solver. Since the underconstrained property can be expressed as a first-order logical formula in the theory of finite fields, and the solver can directly answer these queries, the logical formula encodes a query to check for existence of two different outputs that satisfy the same input. If the solver returns sets, then we know that the circuit is underconstrained. Otherwise, we say the output Y is properly constrained, or simply unique. The other strategy is to statically analyze the constraints of the circuit and use predefined rules and background mathematical properties to quickly detect if a circuit is properly constrained. Consider this example where Y is a linear combination of X and Z. Since Y is linear in X and Z, we can immediately infer that the circuit is not underconstrained. Both approaches have their pros and cons. Statically analyzing the constraint is very scalable and can allow you to verify the large circuits are safely constrained. However, they oftentimes suffer from false positives. So if they say a circuit is underconstrained, it may not be underconstrained. Also, if static analysis can't certify the safety of all required signals from a circuit, it still fails. It's a one-time deal, and partial results may become useless here. And on the other hand, SMT solvers do not suffer from false positives, but have a hard time scaling to larger circuits in finite field. So we propose a new tool called QED squared, which takes as input a set of polynomial field equations and automatically tries to verify that the circuit is properly constrained. The key idea behind our tool is that it combines the strength of static analysis and SMT, allowing it to scale to large circuits while maintaining the precision. At a higher level, the static analysis and SMT phase of QED squared interact in a loop, giving each other information that allows them to make progress they couldn't otherwise do on their own. Regarding the cons from the previous slides, now partial results from one phase can be useful for another. Let's take a closer look. Starting with the polynomial field equation C and a set of signals K known to be unique, the static analysis engine performs the inference and updates the set of unique signals to K prime here. And the invariant here is that K prime should always be larger than K, so each phase always grows the set of signals proven unique. And since our goal is to prove the output signals are properly constrained, if the output signal O are a subset of K prime, then it returns a check mark, indicating the circuit is properly constrained. Otherwise, the new set of unique signals will be sent to the SMT phase. And the SMT phase has a similar interface. It takes as an input K prime and updates it with newly proven unique signals. And there are 4 potential outcomes. The first one is similar to static analysis phase. If everything checks out, then we return a check mark. And for the second, if any of the output signal is proven to be under-constrained, it immediately returns the cross mark, which means the circuit is provably under-constrained. And for the third case scenario, where the SMT phase ends up with the same set of unique signals, which means no new signals are proven safe anymore, and the system reaches a fixed point, then it returns unknown. And finally, if none of the conditions above holds, we then send the new set of unique signals K back to the static analysis phase to repeat the loop. With the interactive loop, we gain benefits. So knowledge from both phases are shared, and multiple turns could scale the reasoning up. So to facilitate a more systematic research and evaluation of ZK bugs, we gathered an extensive benchmark suite from the standard library of the Circom programming language, which is one of the most popular languages for building ZK applications. The suite is called ZK Bench, which contains into the 163 challenging circuits that fall into 3 categories of different sizes and difficulties. We carefully instantiate the templates from circumlib to form a benchmark that covers both the utility templates and also as well as the most security crucial templates from the library. And ZK Bench is suitable for analysis of ZK circuits, as well as bug detection, attack synthesis, and many other security-related tasks. We then perform extensive evaluation over the benchmark set, mainly answering the following research questions. Is our tool effective, and can the tool detect for new unknown bugs in real-world circuits? We focus on 2 metrics, the number of benchmarks solved and the time spent on solving them. And the results gives us a positive answer. So in particular, it solves 70% of the benchmarks with an average of 18 seconds solving time per each. It solves almost 9 out of every 10 small benchmarks and more than 50% of those more challenging ones. As the core benchmark set proves to be even more challenging than we expected, our tool still manages to find 8 serious unknown vulnerabilities from the full benchmark set, which reaffirms that the tool is effective. And we further conduct an ablation study to answer the third research questions by isolating different phrases out from the tool, where 2 additional variants are created that removes SMT and static analysis phase respectively. And our result indicates that both phases are crucial to the tool's effectiveness. Static analysis is more effective in quick verification for large circuits, while SMT is precise in solving difficult circuits, as the benefits brought by SMT in the more challenging benchmark set is more significant than static analysis. This also shows that the synergistic bond between SMT and static analysis is effective. You can, of course, find out more details about our evaluation section in our paper. So to conclude, we propose a new algorithm for automatic checking of under-constrained zero-knowledge circuits. This algorithm combines lightweight static analysis with SMT-based reasoning in an interactive loop that joins the benefit from both approaches. To systematically evaluate ZK bugs, we also collect ZK Bench, which is an open-source benchmark suite that contains an extensive set of ZK circuits from the core circuit building library. And finally, our tool solves 70% of the benchmarks and detects 8 under-constrained vulnerabilities that are previously unknown. Our tool is open source and publicly available on GitHub, so feel free to give it a try. And yeah, finally, thanks for your attention. With all this, I'm also happy to take any questions.
Questions?
Hi, Daniel Genkin, Georgia Tech. Did you try scanning for these bugs in the wild and see what you can come up with?
Sorry, could you repeat the question?
People are deploying these circuits. Did you try scanning around and see if you found vulnerabilities in deployed systems?
So If I understand correctly, you are asking whether I have try to scan the bugs with other security tools.
Try to scan the wide internet with bugs using this tool.
With the tool?
With using your approach, have you tried scanning?
Also, search for the internet.
Yeah.
For other instead of the benchmark sets.
Yes.
I see. So yeah, when we were working on the tool, I think that's actually a good idea. So when we're working on the tools, there isn't so many ZK bugs or ZK circuits existing there. So that's the reason why we just construct a benchmark set and then make the evaluation more extensive. But I think nowadays, there are more benchmarks and more ZK applications there. So that's definitely the next step of our evaluation, and then try out the tool and see whether it works on many real-world applications there.
All right, thank you.
Other questions? So in your loop, is it guaranteed to terminate?
Yes. So it's a kind of a fixed point algorithm, because every time it will just either phase will generate new newly proven signals, and when the newly proven signal is fixed, which means that there is no new information is generated, then it will terminate. So yes, it will guarantee that it will terminate.
Okay. So I guess a related question is, once you find the vulnerabilities, do you have to construct a proof of concept exploit to tell people this is a problem? How do you construct that?
Yes, I have a backup slide here. So this is one example that I can show you the running logs here. So on the right-hand side, I just steal the same benchmark. I just run the static analysis phase, which just infer you some extra information. Mm-hmm. And then eventually I utilize those information and then go to the SMT phase, which will eventually construct an actual counter example, which can be used as an attack vector here to hack into the actual proof. So the answer to the question is yes. Yeah.
Cool. Sounds good. Let me double check. So another question is, when you do the evaluation, you did your ablation study. So is the bug you found in the QED squared is a proper superset of the other two, or there's non-overlapping bugs you found? You see the bar graph that you have,
here?
For example, is the 69 bugs strictly included in the 83 bugs, or the 69 actually find different bugs than the 83?
I think there are overlaps here. So because for the two phases, SMT and also the static analysis phase, both of them can independently solve some benchmarks. And then when we add them together, it creates some synergistic effects that allows the tool to even scale up to more difficult benchmarks here. So I think to answer the question, there are overlaps here, and then we gain benefits by combining them into an interactive loop.
I guess my question is more about the non-overlaps. Are there bugs that found by SMT or the other method, static analysis only, that your tool somehow failed to find? Is it possible that somehow SMT alone worked, but your tool somehow just missed it?
I think theoretically this is not super possible, because our tool combines the SMT approach and static analysis together. So whatever can be solved by SMT.
Yeah, but if you look at the data, you know for sure that the 69 is a proper subset of the 83 bugs. Mm-hmm. If you just look at this graph, every single bug that's in the orange bar and in the red bar, they're included in the blue bar.
Mm-hmm.
Okay.
Yeah, correct.
Cool. Any other questions? Let me check online. All right, if no questions, let's thank the speaker. So this is actually the end of this session. So we have a break coming up. There's virtual PLT. Also, after the break, we have the plenary session by Professor Margaret Martinosi. I'll see you guys over there. Thanks.